Bismillahirrahmanirrahim. This is a static loading problem of a bolted connection, and the problem statement is here. The dimensions are also given. Essentially, these bolts, which are 10 in number, they are compressing this confined gasket to make sure that the internal pressure it is maintained and the gas doesn't leak. And the dimensions are all given. We are supposed to find out the size of the bolt for this, and also the safety factors, yielding factor of safety, load factor, and the joint separation factor. This diagram is a bit misleading because as you can see, A and B both are 20 millimeters, but the diagram doesn't suggest so. But because this diagram is a generic diagram for many problems, so don't worry about this. Just accept the numerical values. Now, to make it easier for ourselves, let's draw this relevant part of this here. There's a bolt head, there's a bolt, and then you have this nut here, and a part of bolt will come out, and then you have two plates that are, for our case, they are equal in thickness, and then the rest of it. So if I draw this bolt part only, it will be helpful for us in doing the first part of the problem. So this is your bolt with a nut, and what is happening here is part of it will have threads like this. So talk about the different lengths of the bolt. This is total length L, and we are supposed to find this one, and the length of the threaded part inside the grip, that is LT. Please brush up on the basics. This is one of my lectures on these things. And then part of the unthreaded part of the bolt inside the grip length, that is called LT, and the total threaded part of the bolt, that is LT. Now this is the nomenclature. Now let's start with, and we have to find out the total length of the bolt. So the grip length, first of all, grip length in this case L is equal to, you have 20 millimeters plus 20 millimeters, 20 plus 20, 40 millimeters. Now, total length, this total length that we need to find out, that has to be greater than or equal to this grip length plus H. Now this H is the nut height, because we want to utilize the whole, all the threads inside the nut, they must engage. Now in table A31, against a bolt size of M12, M31, M12 size, against this we can read that nut height H is equal to 10.8 millimeters, because this M12 is given to us, so we don't need to worry about this one. So this L has to be, in this case, L must be greater than or equal to 40 plus 10.8, that is, it must be greater than or equal to 50.8 millimeters. Now this is the ideal situation. If we can get slightly larger than this, so that 2 or 3 threads come out of the nut, should be enough. But as it happens, we don't have bolt lengths available in all sizes. So when we go to table A17, that is preferred size, table of preferred size, we find out that after 50.8, the next preferred size is 60. So we have no other option but to select a bolt length of 60 millimeter, and that will be available too because it is one of the preferred sizes. Now this L is known to us. What about LT? Because we will be needing these LD and LT, small LD, small LT, because we are going to use these values for stiffness calculations. So let's get these things out of the way. LT is equal to 2D plus 6 in the case of lengths less than 125 millimeter, and because this is less than 125 millimeters, so this is applicable. By the way, this is equation 814. So put in the values to, this is M12, so D is 12 plus 6, this is 30 millimeters. So LT turns out to be 30 millimeters. Now we come to this LD. Because LD and LT, these two things are important for us for stiffness calculation that we are going to use. Now LD is simply, as the diagram suggests, LD is simply L, this total L minus this LT. So L minus LT, and you have 60, which is the length, minus 30, which is LT, threaded length. So LD is nothing but 30 millimeters. Now if LD is known, then LT is very easy to calculate, because this LT is basically total grip length L minus LD, grip length, that is LT, L grip length minus LD, grip length was 20 plus 20, 40 minus 30. So this gives us LT is equal to, this is the threaded part of the bolt inside the grip length. If we have these values, then we can proceed, because ultimately the first part of the problem was select a suitable bolt length from the preferred size, that we have done, L. But now this information, a certain L, and which will give us a certain LD and LT, small LT, they are going to be used for the calculation of stiffnesses, because stiffnesses will give us C, point constant, and then C, with C in hand, we can calculate NP, NL, and all those things that are required. So for us, these two values are of importance, LD and LT. Now, if we are going to find out the stiffness, KB and KC, and then to find out C, then we also need the areas of the threaded part as well as the unthreaded part. So let's take those up now. Area of the unthreaded part or the shank part is very simple, 5/4. So this is the nominal diameter, and just using the cross-section area of a cylinder, and that comes out to be 113.1 square millimeter. AT is even simpler. Read it off table 8.1 against a size of M12. Make sure that you read it against M12 into 1.75, the pitch, because the tensile stress area, they are also different for different pitches. So this turns out to be 84.3 square millimeter. Now with these four values, it's very easy to find out KB. KB is AD, AT, E over AD LT plus AT LD. These formulas, you can look those up, these formulas up in your textbook, and you can also consult one of my previous lectures. So these are all there in detail. So putting in the values, all the values, this is steel, so steel has this Young modulus 200 GPa. Then you and this turns out to be I converted GPA into MPa, and all the other areas and lengths are in millimeter or millimeter square, so I get value in Newton per millimeter. So please be consistent in this. You can use any set of the units, but be consistent. Now we come to the slightly more complicated and probably the most tedious part of this problem, because the rest is very easy, and that is the calculation of Km, the members. Let's make our life easier by drawing roughly the situation here. This is the head of the bolt, then you have the nut, there's a bolt here, and you have then the two plates. Now luckily for us, the two plates both are, although of different materials, it's true that they are of different materials, but they are of the same thickness. If the thickness was different, we would have had to calculate maybe 3 times. Recall the concept of the frustra. Here we only need to calculate 2 times, because something like this happens. The stiffness distributes like this, and all you need to do is first calculate stiffness K1 in the first member, and then you find out the K2 in the second member. That is only possible because although we have the two different materials, but the thickness is the same. If it was the same material, then it doesn't matter how many plates are there and what are the details of the thickness of each, doesn't matter. So let's calculate K1. We are talking about the first plate first. The formula, again, you don't need to learn this by heart, you get it in your textbook. Slightly tedious part of the problem, but there's nothing difficult about it. Maybe slightly boring, but not difficult. Now put in the values. 0.5774 into pi. The upper plate, this one, this is steel, so 200 is GPa is the Young modulus. I've converted into MPa into 12. 12 is the diameter, small d. Now when it is small d, we're talking about this one, the inner diameter. And then we talk about, when we come to the big D here, let's fill in the figures. .155, D is 20. D, this is, we are talking about this D here. So this is simply 1.5 times of D. So 1.5 times of D is 12, so it is 18 minus D 12, and this is 18 plus 12 over 1.15520 into 20 plus 18 plus 12 over 18 minus 12, and this turns out to be slightly a big number, 4318945.5 Newton per millimeter. Now this is K1. Now we're talking about this plate 1. Now this is plate 2. We have to come to the second plate now, and There's a shortcut way of doing this, because only difference between plate 1 and plate 2, thanks to the fact that we have a certain kind of symmetry here, the only difference being E, Young modulus E, and it's a cast iron instead of steel. So we go to table A24 against cast iron class 30, which is given in your question statement. E for this grade is 100 GPa, and 100 is a very good number. It's exactly half of the Young modulus for steel, grade 30. Now this 100 is exactly half of the first, the 200 of the steel. So K2, you don't need to go into all, because all the other dimensions are the same. In this case, your D will be, the big T will be this one, but how is it different from the from this T? There's no difference. So everything else is the same. So it's very easy for us. K2, because this E comes into the numerator, so simply 100 into K1 over 200. In other words, it is half of the K1. So K2 is 2159472.8 meter per minute. Now we're talking about Km. When we talk about Km is because these are in series, 1 over Km is 1 over K1 plus 1 over K2, or Km is equal to 1 over K1 plus 1 over K2 inverse, which turns out to be, and you can put these values of K1 and K2 and you get this 1439648.5 newtons per millimeter. 1439648.5. Yes. So you have the values of Km as well as Kb. Kb, recall, 521001.6. So now we can calculate the value of C, and the most time consuming part of the problem is already done. So C was, again, recall the formula, Kb over Kb plus Km. Put in the values 5210001.6 over 5210001.6 plus 1439648.5, and the C then is 0.266. This is an important number. Let's take up the three factors of safety. First of all, yielding factor of safety, NP. So recall the formula, SPAT over CP plus FI. The other one is NL, SPAT minus FI over CP, and the third one, N0 is equal to FI over P1 minus C. Now we have the value of C with us. We also have the value of AT. So this is, we know, C is known. What about Fi? What about Fi? We don't know Fi. So Fi, we know that it is, if we recall equation 831, it is 0.75 into Fp. This is equation 831. Why 0.75? Because this problem is one where we are using a gasket here, and you may need to unfasten this joint, replace the gasket, then fasten it again. So by definition, this is not a permanent joint, it's a temporary joint. And what about Fp? Fp, obviously, Fp is a function of proof strength multiplied by the tensile stress area, and this is equation 832. Now proof strength, we know the material, so we go to table 811, and against a grade of 9.8, class 9.8, because this voltage of class 9.8, we read that SP is 650 MPa. Now if it's 650 MPa, AT we already know. Putting in the values, Fi becomes 0.75 into 650 into 84.3, which is 41096.3 Newton. This is the value of Fi, which means that now we know this Fi. This one is known, this one is known, SP already known, SP, this one is known, AT is also known, C is known. So we only need P to be able to calculate all these factors of safety. And what is P? P is the applied load, and we have to see what kind of applied load is acting on this problem. Once these bolts are tightened and Fi is created, the rest of the load that acts on it, which is the applied load, that is because of the pressure, which is 6 MPa. And obviously this is going to act everywhere. It will also act here. This P, 6 MPa, this tends to lift this head upwards, and it's a simple matter of calculating the P by multiplying the 6 MPa with the area. And this it would be tempting to use the C as a diameter for that area, but you have to see that we have been given an effective sealing diameter D, which means that this gas has been confined to this region. It cannot go beyond this. But if you were to use this inner diameter, it would be a mistake, because the fluid will be acting inside this effective sealing diameter. So we have to use this D for our calculations. You need to be careful, because sometimes it's easy to make a mistake here. The rest is simple. First of all, let's calculate the total P. Let's call it P total. That is the total force upwards. That is simply pi by 4 into 150 square, which is the effective sealing diameter, multiplied by the pressure 6, and this turns out to be 106,028.8 newtons. This is the total load applied. Recall that there are 10 bolts, so P per bolt will be simply P total over N, which is in our case 10, because we are going to deal with one bolt, and that turns out to be 10602.8 newtons. Now the rest is simple, because now we also know this P. P is known, P is known, P is known here. So all it needs is for us to plug in the values. So let's do that now. So first talk about this yielding factor of safety. Let's take this up first. And P is equal to SPAT over CP plus Fi. This is 650. All the values are known now. 84.3. C is 0.266. P we just calculated, 10602.8. Plus Fi is 41096.3. And P is equal to 1.25. It may look like a small factor of safety, but if we consider that we are talking about minimum proof strengths, and also the fact that the proof strength is still lower than the yield strength. Actually, it's not that bad of a factor of safety. Now we take up the load factor of safety, or the load factor, and that is NL SPAT minus F. These are just the formulas that we saw earlier, like the CP 650 into 84.3 minus, in this case, 41096.3 over 0.266 into 1060.8, and NL turns out to be 4.86. The difference between this NP and NL, of course, being NP is applied to the complete stress, that is the stress caused by P as well as the stress caused by Fi. But as far as this load factor of safety is concerned, this only applies to the applied load. It considers the preload as something that is there. Now we come to the last of the factors, separation factor of safety. Again, N0 Fi over P1 minus C 41096.3 10602.8 1 minus 0.266, and this turns out to be 5.28. Again, this, of course, by definition, this applies to the load P. So this 5.28 is the factor by which load P can be increased before the joint will separate. This NL 4.86 is this is the factor by which again load P will have to be increased before proof strength is reached. That is, yielding will take place. And this NP is 1.25. This is a factor by which the total stress, that is stress caused by P as well as stress caused by Fi, the combination will have to be increased before yielding takes place. Thank you.